In this video, I will make the reagent Thiophosgene, which is a bloody red toxic liquid and very useful for different chemical transformations. However, it's expensive and not widely available. Therefore, I want to try to make it myself from more accessible chemicals. And for this video, I will show my first attempt, along with recommendations to improve the method. Thiophosgene is mostly used to make isothiocyanates from primary amines, which can for example be converted to thioureas, as well as for the esterification with alcohols, like with catechol, to form thionyl-benzodioxyls. These are convenient for making fluorinated benzodioxyls, as brought to us by the research of Dr. Josiah Newton, aka that chemist, who is such a big fan of drugs, he even fried his brain with them. We love the commitment to chemistry. Other than that, it's just a very cool reagent, purely for its looks. And it has the smell of meat to the point of nauseating. So let's get started. First, I will need chlorine gas for this reaction, so I have to prepare a generator. This can be done with good old pool chlorine tablets, which contain the chemical trichloroisocyanuric acid. When it reacts with hydrochloric acid, it liberates chlorine that can be used for the reaction. The most convenient form is a powder, but they often come in tablets. Some hard as bricks, others fairly crushable. These are luckily of the fairly crushable variety. So I can put them all in a plastic bag, which I put in another plastic bag, and I then pulverize the tablets by hitting them with a hammer. When that's done, I pour it all back into the original container. I then set up a large 3-neck flask in which I put all of the crushed tablets, which is 1 kilogram. Now that is set up, I set it aside while I prepare the reaction mixture. For this, I have set up a flask with a thermometer in an ice bath. And I also set up a gas washing bottle filled with concentrated sulfuric acid to bubble the chlorine through, which will remove water from the gas stream. Now as the first reagent, I add in 250 ml of carbon disulfide. This is probably the most difficult to get of all the reagents in this video. It is difficult to produce, it isn't super available because it isn't used that much, and it's a bit expensive. However, recently it has gotten more accessible. It is not a restricted chemical, so it shouldn't be an issue to acquire it, if available. Then as the catalyst, I add in 1.2 grams of iodine. A diketone, such as acetylacetone, can also be added to prevent the formation of side products, and it allows for the reaction temperature to be raised. However, I didn't try that. It is said that it will mostly inhibit the negative effects of iron contamination, as well as prevent formation of disulfur dichloride. I stopper the flask and I connect the tubes to the generator and gas washing bottle. On top of the generator flask, I have added a dropping funnel with concentrated hydrochloric acid, and every neck is stoppered. At the end of the tubing, I have wrapped the tube in Teflon, jammed it in an empty syringe, and connected the syringe to a steel needle. However, this is a large mistake for this reaction. The steel needle will quickly corrode and form iron chlorides. For many reactions, you can sacrifice a steel needle for this if it doesn't matter, but here it will also react away the iodine to iron iodides and slow down the reaction. Also, like I mentioned before, iron is bad for this reaction and causes the formation of various byproducts, like Thiophosgene, but we don't want it here yet, since it wouldn't be possible to separate it from the sulfur chloride that is produced. The added acetylacetone won't be able to save me from this relatively large amount of iron. Instead, for this reaction you should either use a glass gas inlet tube or a Teflon tube. Ideally, something that produces many small bubbles for a maximum surface area, as the mixture doesn't absorb chlorine that efficiently. But maybe that's because I used a steel needle. However, that still brings me to my second point. If the absorption of chlorine isn't super efficient, it is best to set up a trap for the unabsorbed chlorine, as emitting it, even with a few mud, is very annoying, since it corrodes the lap stand and other random things, which will then absorb moisture from the air and start leaking juices. Anyhow, I just gradually dripped in the hydrochloric acid and bubbled the chlorine into the mixture over several hours. I did prematurely stop this reaction, as in without reacting all the pool chlorine, as I didn't like emitting a lot of chlorine, and I also already contaminated it with iron, so I suspected this would be an educational run. In this reaction, carbon disulfide is chlorinated completely to form perchloromethyl mercaptan and sulfur chloride. If we ignore the catalyst, we can say chlorine attacks the carbon disulfide continuously until all positions are chlorinated. But in reality this is aided by iodine, which reacts with chlorine to form iodine monochloride that is a lot more reactive. and will form iodinated intermediates or directly by the reaction of iodine with chlorinated intermediates. This iodinated end product will all convert to their fully chlorinated version by reacting with chlorine, forming iodine or more iodine monochloride, which continues the reaction. The role of the diketone acetylacetone is said to be mostly to inhibit the formation of disulfur dichloride, which also messes with the reaction, and it is also supposed to negate the effects of trace iron that is a common contaminant in industrial-grade carbon disulfide. When I felt like I was done with it, I just disassembled the setup. I then set up the flask for distillation, first distilling over unreacted carbon disulfide together with sulfur chlorides and potentially Thiophosgene carbon tetrachloride and iodine monochloride. First it came over as a red liquid, perhaps because of presence of Thiophosgene, and then an even darker red liquid. We can already see that most of the distillate is unreacted carbon disulfide and impurities, since it mostly distills over at the boiling point of carbon disulfide. I distill out the rest of this under a vacuum. The desired product, perchloromethyl mercaptan, has quite a high boiling point, so everything else can just be distilled off first. After a while, the mixture in the reaction flask clears up and becomes more of a yellow-orange, which is the color of the desired product. So when that starts to distill over, I remove the vacuum, clean out the apparatus, and attach a new flask. I then vacuum distill over all of the product. It comes over as a yellow-orange liquid with a very pungent and acrid smell. But its vapor pressure isn't too high, so it doesn't fume that much and it isn't easily noticeable. It was actually once used as a chemical weapon, but it turned out to be not so effective because guess what? It can decompose in the presence of iron and it is easily filtered by carbon filters. So, in the end, I am left with 41.6 grams of the perchloromethyl mercaptan, which is a yield of 5.4% from the amount of carbon disulfide added. It's not the best, but we saw all what has been done to it. At least I have something to continue with. If you want to check the progress of this reaction, the reaction can be interrupted and the reaction flask weighed, where you can see approximately how much chlorine has been absorbed, if you leave it closed. Before I will make Thiophosgene from this product, I will clean up the previous distillate and recover the carbon disulfide, which can be reused, preferably for the same reaction. For that, I move all of the distillate to a separatory funnel and wash it with a solution of sodium thiosulfate to destroy any chlorine and iodine. I then wash it with a concentrated potassium hydroxide solution, which should accelerate the destruction of sulfur chlorides and thiophosgene. It clears it up significantly and expels a bunch of sulfur, but the contact time needs to be longer. It would be annoying to do it with shaking, so I transferred it all to a flask, to which I add more water and potassium hydroxide solution. After stirring strongly for a few minutes, the color improves a lot. And after already decanting off most of the water, I separate the rest of it in the separatory funnel and return it to a flask. Then to remove remaining water, I add some calcium chloride, which will absorb it. I then filter all of it through some cotton into a flask. And I set this up for distillation. I distill off the carbon disulfide, which has a low boiling point, and it comes over as a slightly yellow liquid, leaving behind an orange-red liquid. Pure, it would be colorless, and perhaps there's another good treatment that can be done to make it so. But in this case, it seems sufficient for potential reuse in the same reaction. I collected 212 grams, which is 67% of the starting material. It is quite easy to recover unreacted carbon disulfide, but if the reaction is run properly to completion, there should barely be any left. Now that I have salvaged the majority of the starting material, I can't be blamed for the low yield, so I can continue with the next reaction to make Thiophosgene. For that, I set up a flask in a heating mantle, to which I add 200 ml of the solvent silenes, which I already start heating to a reflux. As the catalyst, I add in 1 gram of iron 3 chloride. Now it seems obvious why iron is bad for the previous reaction. When it has mixed, I add in 41.6 grams of the perchloromethyl mercaptan at once, and quickly add a fractionating column as well as a short path distillation apparatus on top. The reaction starts quickly and the mixture begins to darken. Then it becomes a lot more violent, starts to boil, becomes black, and expels a very large amount of hydrogen chloride. I just keep heating it at reflux temperature, and gradually the condensate in the column becomes more and more red from the Thiophosgene. After insulating the bottom part of the column, the Thiophosgene starts to distill over as an orange-red liquid. I continued that until it no longer came over. In this reaction, perchloromethyl mercaptan is reduced to Thiophosgene through a radical mechanism catalyzed by iron 3 chloride, while consuming xylene, forming a mixture of chloroxylenes and hydrogen chloride. When it's done, I am left with a red liquid containing thiophosgene. Since I can't be sure of its purity, and almost certainly it carried over some xylenes or even starting material, I will redistill this. After doing so, I am left with 15 grams of thiophosgene, which is a yield of 58%. Thiophosgene costs about $270 for 100 grams, while you can get 1 liter of carbon disulfide for less than that. The rest of the reagents used are very cheap, so if the reaction is done properly and on a decent scale, it is probably quite cost efficient. That was it, bye.